Now, as promised, we're going to use L'Hopital's rule as needed to find limits. And we're going to, in particular, concentrate on limits that look like one of these things. These are called indeterminate forms. And again, it's nothing you should try to memorize. There's no memory needed. If you add two things together that are both going to infinity, they're both getting big, and you add them together, well then of course the sum is going to get big. There's no mystery to it at all. But what if you have one big thing subtract another big thing? Then it depends on what those big things are. The limit could be anything. What do you want the limit to be? 17? Let's choose it to be 17. There's a simple one. Just subtract off the x's. And this number here, this function is always going to be 17 greater than this one. So the difference will always be 17. So simple, no big deal. Here's another one that isn't so simple, but the limit is also 17. I know that's going to be because we did this one a while back, and the answer was 1/2. And so I just know from thinking about it that if I had a 34 here, it's going to be 34 over 2, which is going to go to 17. So anyway, so those are things of the form infinity minus infinity. Okay? Now, how about something of the form infinity over infinity? Okay? Where would you use those? Well, of course, we've already done important ones. We did this one. We did that one, I think, last time or 2 times ago. And this, after taking L'Hopital's rule 5 times, we ended up, that thing went to 0. This grows faster than any power of x. We also looked at the limit of ln of x over x. And we noted that x grows faster than ln of x. It grows slower than even any root of x. So this thing goes to 0. So there's a couple of the form where we needed L'Hopital's rule. If you wanted to do one that went to 17, this goes 17x divided by x, as x goes to infinity, right? That goes to 17. So my point is, any of these things could be anything. They could be 0, infinity, 17, -5, e, whatever you want them to be. Okay? What about 0 over 0? We did one in the last lesson, which was kind of interesting. This thing went to, remember, that was the ln of 5/2. So there's an interesting case where both the top and the bottom were 0 over 0, so we use L'Hopital's rule on it. Again, we wouldn't have to use L'Hopital's rule. We could do 17x over x. As x goes to 0, both the top and the bottom are going to 0, but the ratio is going to 17. So, so no problem there. Okay? How about 0 times infinity? And again, you should realize that the reason why these are indeterminate forms is because there's tension. These things are fighting each other. Which one of these things is growing faster? Which one of these is growing faster? Which one of these is going to 0 faster? Is this thing getting small faster, or is this getting big faster? Which one's going to dominate? So again, you could do a simple thing like 17 over x cubed times x cubed. This thing's going to 0. This thing's going to infinity. The ratio is going to 17. So again, we can get any answer we want. But let's do another one that's a little more interesting. We did x times the ln of x in the last lesson. And we saw that thing ended up going to 0. Okay, so that was one where we needed L'Hopital's rule. Let's try another one where we'll need L'Hopital's rule. This is one of my favorite ones. Notice as x goes to infinity, this thing's getting big. big. This is approaching the element of 1, and the element of 1 is 0. So this is approaching 0, and that's going to infinity. So it's an interesting problem. There's tension. Which one's going to dominate? Is this going to dominate and bring the whole thing to 0, like it did here? Is this going to dominate and bring the whole thing to infinity? Or are they going to kind of, as it were, cancel each other out or compromise, as it were, and come to something between 0 and infinity? So remember the trick we did last time? We said, okay, in order to use Hopital's rule, we can write it like that. Now as x goes to infinity, this thing goes to 0, and so does this thing. Agreed? As x goes to infinity, they're both going to 0. So we can use Hopital's rule. By the way, generally you take the simpler looking one and put it downstairs. If we put this thing downstairs, we'd have 1 over the ln of that, and by the time you took the derivative of that whole thing, it would be kind of messy. So that's the general rule. So here we go. Take the derivative of the top. Derivative of the ln of anything is 1 over that thing. Times the derivative of the inside. The derivative of the inside is negative 1 over x squared. Now you take the derivative of the bottom. That's going to be minus 1 over x squared. This cancels exactly with this. As x goes to infinity, this is going to 0. 1 over 1 plus 0 is 1. Interesting. So here's one where the answer compromises. It doesn't go to 0. It doesn't go to infinity. They kind of compromise, and the answer is 1. Okay, very good. Let's try this one. What's the tension there? 1 to any power is 1, right? 1 to any power is 1. So if this thing were actually 1, then the answer would be 1. On the other hand, you take anything even a little bit bigger than 1, and you take it to higher and higher powers, and it's going to go off to infinity. So this thing is trying to pull this thing up to infinity. This thing is trying to carry it down to 1. Which one wins out? Which one wins? You want to guess? And here's the problem we're going to do. I'm sorry. Right there. Do you agree with me? As x goes to infinity, this thing in here is approaching 1. This thing in here is getting really, really big. And so these two things are fighting. Does this win? Taking it to infinity? Does this win taking it to 1? Or are they going to compromise? Well, remember the first thing I taught you in the last lesson. Whenever you have anything to the x power, you can rewrite it as e to the x times the ln of this. Okay? So this thing is just the same as this thing. I haven't used Hopital's rule on it yet. I've just algebraically written this in a different way. And then recall this is a continuous function. Recall what I said about continuous functions. When you have continuous functions, you can basically bring the limit inside. Okay? We said that f is continuous at a if the limit of f of x as x approaches a is equal to f of the limit of x as x approaches a, which is equal to f of a. Basically, something is continuous if you can bring the limit inside the function. So this is a continuous function. I can bring the limit inside up to here. Okay, so now we just have to evaluate this limit. Any idea what that limit is? Notice it's of the form infinity times as x goes to infinity, this is going to 0. Infinity times 0. So it looks like this is a candidate where we might use L'Hopital's rule. Again, I love doing this in class. I ask the class whether they happen to have ever seen this limit before. Most of the time, most everyone says no. And then I say, look right above you. There it is. There it is right there. We just did it. So that's equal to e to the 1, which is e. How interesting is that? So this limit right here is equal to e. And remember, I mentioned that to you way back when we first introduced the exponential function. I said e was this very special function that satisfies this particular limit. So very interesting. Okay, so there it is. And this is a very important problem. This is used in compound interest, instant interest, things like that. It's used a lot. Okay, 2 more. Here's 0 to the 0. I'll get rid of all these now. There's the most straightforward one, I guess. Let's just take x to the x power. Why is this an indeterminate form? Think about it. 0 to any number, no matter how small it is, 0 to any power is equal to 0. On the other hand, you give me any number, no matter how small it is, and you take it to the 0 power, that's equal to 1. So what happens when both of these things are happening at the same time? This never hit 0, that never hit 0, but they both approach 0. This thing's forcing it to 0, this thing's forcing it to 1. Does 1 win out, or do they compromise again? What would they compromise to? Between 0 and 1? How about 1 over e? Wouldn't that seem like a reasonable compromise? Let's see once what happens. Well, here we go. Remember the definition? That's just e to the x ln of x. And this is the one that you did in the last lesson. And so that's the limit. I won't do it again. That's the one that went to, as x goes to 0, this thing went to minus infinity, this thing went to 0. We put ln of x over 1 over x, and I won't go through all the steps again, but just a couple more steps, and anyway, that ends up being e to the 0, which is 1. So in this case, one of them wins out. Anything to the 0 power is 1. That ended up kind of winning out. So there you have that one. And finally, what about something of the form infinity to the 0 power? Notice, as x gets big, the bottom's getting really, really big. The top is approaching 0. Let's think of it again. If you take any number to the 0 power, no matter how big it is, it's equal to 1. On the other hand, if you take some number to anything any bigger than 0, like this, and you keep making this number bigger and bigger and bigger and bigger, then you take the 1,000th or the 10,000th root of this, it's going to go off to infinity. So which one wins out? Does the exponent win out again like it did there? Or do they compromise this time? Okay, maybe this one goes to e. Something between 1 and infinity. Well, here we go. It's fun to guess at them. So e to the 1 over x times the ln of x, which is equal to the limit, equal to, I'll bring the limit upstairs again. You're going to get the ln of x over x, and this is the one I did 2 lessons ago. That's just going to be 0. E to the 0, which is 1. So there's one that goes to 1. So these are all the indeterminate forms. As I say, don't memorize them. Just realize, just think about why when you have something of one of these forms, you just can't see the answer right away. This one right here, if we had written this as 1 plus b over x, all to the c over x power, this would, check it out yourself, this would have ended up being e to the b times c. So by altering what b and c are, I could make c equal to 1 and b equal to the ln of 17. And so I'd end up with e to the ln of 17, which is just 17. See that? So again, any of these forms, you can make them be whatever you want. So never say 0 or infinity, just as a quick reaction. Always think about, well, we're going to have to do something in order to find the answer. Okay, good stuff. Really good.